This video is about question 5 and 6 on the homework. Kind of 5 is preparation for number 6. So let's do look at the answers to question 5 first. So question 5, the table in week 5, lecture 3 under bar 2, that handout that we were going to do in class, but again, kind of didn't have enough time. So this is filling in this table. And this is just finding the R in, R out, gain, GM, and whether it's inverting of each amplifier. And if you want to go through and do this on your own, go do it right now. Otherwise, I'm going to fill this in. So for R in of the common emitter, it's going into the base, there's no degeneration. So that R in is R pi. Your R out, you see RC and a collector. Remember the quick method, doing the quick method, you ground this, and then if you're trying to find R out, you find the output. You sit on the output and you see how many paths to ground, and there's 2. There's one through the transistor where you hit the collector, and one through RC. So this is actually RO parallel RC. Okay. GM for a common emitter, it's inverting, so it's negative GM. And then the gain is just your big GM times your R out. Okay, for a common collector, your R in is this more complicated equation because there's a resistor below the emitter. You have this higher R in. The R out, again, to find R out, you find the output node and you ground the DC source, and you've got 1 over GM looking up because you hit the emitter and RE. So this is 1 over GM parallel with RE, but 1 over GM is so small that it's in 99 cases, you can just write that as 1 over GM. 99 cases out of 100. And then your GM, since there's no extra resistors over what the circuit is. This RE is below the emitter, but it's not degeneration. It's part of the circuit itself. And then your gain is your big GM times your R out, which is 1 over GM, which equals approximately 1. Okay, and it's not inverting. Okay, common base. Common base, your input goes into the emitter, so it's 1 over GM. Your R out, you look in both directions and you get, I'm going to write RC first so I don't have to do the capitalization thing, RO, and your GM, there's no degeneration, no resistor below the emitter, and it's not inverting, so it's a positive GM, and you get the same gain as you got for the common emitter, except not inverting. Okay, common source. So the common source amplifier is this one. Common source, the input goes to the gate, and so that's infinite. No current goes into the gate. Your R out is the exact same thing as common emitter and common base. I wrote RC, I guess it should be officially RD. It's inverting, so you have a minus GM. It's paired, it's friend in the BJT world is the common emitter, which is drawn right above it. And then your gain is your big GM times your R out. Okay. You should be noticing that everything except inputs into the gate look exactly like their counterpart in the BJT world. Okay. So common drain, that's this amplifier right here. Common drain, your R in is infinite. Your R out is looking up. You hit the source, which is 1 over GM. And that's, so looking up, you hit the source. Looking down, you hit RE. But again, because 1 over GM is usually much smaller than anything else, you can usually approximate that as 1 over GM. It's not inverting, so its GM is just GM of your transistor. And then your gain is your big GM times your R out, which gives you approximately 1. Okay. And last but not least, this is going longer than I planned because the table's taking time. But I'll separate the table and the, no, I'll just keep going. Okay. Last one is a common gate. Now, common gate, the input goes into the source, so source is 1 over GM. Then your R out is RC parallel with looking down, which hits the drain, and the drain is RO. And then your GM, no degenerations, so it's just GM, and it's not inverting, so that's a positive GM. Oops, that goes here, sorry, my bad. And then the gain is your big GM times your big RO. Darn it. Right, see if any other, yeah, I'll post this afterwards. Okay, so the first questions on the homework, that was for a single transistor amplifier. So one of the ones in this table, or one of the ones in this table with a slightly different flavor, like common emitter with degeneration is a flavor. Common emitter with passive load, common emitter with active load, common emitter with degeneration, common emitter with degeneration and active load. Those are all different flavors. And so these, pretty much what I want you to do is just look at the table and remind yourself what the characteristics of each of the single transistor amplifiers are. Okay, the next question, question 6, is actually, some people think it's fun. I think it's fun. So now you know the amplifiers that are available to you. Those 6 amplifiers and their flavors are available to you. And now your boss comes in and asks you to design some kind of amplifier that can't be solved with a single amplifier. So for example, if your boss says high gain and low R out, you don't have a single you don't have let's go back over here. No, it's 5. You don't have a single amplifier like a common emitter. It gives you the high gain, but it has a high R out. If you do the common collector, oh, it has a low R out, just like your boss asked for, but the gain is very small. So the question in question 6, you can't do this with just a single stage. You have to cascade amplifiers. And amplifiers, when you cascade them, their gain multiplies. So if I cascaded 2, if if I cascaded two common emitter amplifiers, I know the gain for a common emitter amplifier is GM-RO parallel RC. If I cascaded two amplifiers, the first amplifier's gain is this, you'd multiply the gains of each stage, and your final gain would be the product of these two, just like you did when you were doing loading factor. Okay. So if you had two amplifiers, A1 going into A2, the net gain from the input to the output would be A1 times A2 is your total gain. Okay. So don't want to do these questions. I forget exactly what's on there, but let's just do a couple of examples, and that should be enough to get you started. So let's use the example I just said, that nice high gain. Let's do high non-inverting gain with low R out. Okay, you don't have to do these quite in order. If you see low R out, you automatically know that you need a common collector or a common drain. If you're doing MOSFETs, it would be a common drain. But now you have your low R out. That gives you low R out. But you don't have high non-inverting gain. So there's actually two solutions to this. You know that common base, since there's no specification for Rin, you don't care about what Rin is. But you could do a single common base, and a common base has a pretty large gain. The gain of this one's one common base or common gate. And so now this is non-inverting. So your output, if this goes up, and this goes up, since none of these are inverting. And that's a perfectly valid solution. But you could also say, okay, well, if I invert twice, and then put it through a common collector. Now this inverts, so now if you give it an input that goes up, the output of the first common emitter goes down, but then the second common emitter flips it again, and the common collector isn't inverting, so you're going up. And so from the input to the output, it's non-inverting, which was part of the spec. Hopefully that's enough to get you started on that question.